No one is here yet, so I think we'll wait for 5 more minutes for someone to join, and then we'll start with today's class.
Okay, welcome to the week 7 of problem solving session of heat transfer, whose instructor is Professor Sunando Dasgupta at IIT Kharagpur, and myself Kalpita Nath. I am research scholar at IIT Kharagpur itself. So, without further ado, I'll share with that is from the previous session of week 6, we had one question left unsolved. So, we'll start with that question first. Let me share that. Yeah, I think it's visible and I'm properly audible. So, let us concentrate on this question first. So, what is said that water is need to be heated from 15 degrees Celsius to 65 degrees Celsius as it flows through a 3 centimeter internal diameter of 5-meter long tube. The tube is equipped with an electrical resistance heater that provides uniform heating throughout the surface of the tube. The outer surface of the heater is well insulated so that a steady state operation, heat is generated and heat is transferred to the water through the tube. That is here constant surface heat flux is maintained. So we can use a condition for that. And okay, if the system is provided hot water at a rate of 10 liter per minute, determine the power rating of the resistance heater. So we have to find what is the power rating of the resistance heater. That is what is the power rate of power that is transferred by the heater that keeps a constant surface heat flux, right? And also the inner surface temperature of the pipe at the exit. Okay, so this was the previous day's question. So we'll give it some time and then we'll come up with the solution for that. So let us give it 3 to 4 minutes and then we'll go on with the solution. Okay. As I've already explained in previous day, if you look into the recorded video of previous day, I've already explained how to solve it. So let us just simply proceed with the solution. So, it's question number 13 of previous day. Writing pad is visible, right? So first we'll go on with the cross-sectional area, that is 1/4 of pi d square. 1/4 of pi, diameter is 0.03 meter, whole square, that is 7.069 into 10 to the power minus 4 meter square. Okay, then is the surface area, that is heat transfer area. That is heat transfer area is the perimeter into length, that is pi dl, that is pi into dia is 0.03 meter into L is 5 meter, that is 0.471 meter square. Now the volumetric flow rate, so that is m dot is equal to rho v dot, that is 992.1, that is density kg per meter cube, into volumetric flow rate is already given 0.01 meter cube per minute. So we'll just convert it to like this will be 9.921 kg per minute. We'll convert it to second. 0.1654 kg per second. Okay. Now the heat transfer rate. That is Q dot is equal to mCp delta T. That is outside minus inside. Okay. This is entry. This is exit and this is in entrance. So this is the total heat transfer that is transferred between the exit, like how the temperature have increased. When it was the water was at the inlet, its temperature was 15 degrees Celsius, and when it was at the outlet it was 65 degrees Celsius. So how it has gained energy, that energy is the heat transfer rate, and we can simply calculate it from mCp delta T, and we have already calculated from the volumetric flow rate, right? Sorry, the volumetric flow rate is 10 liter per minute, it's given, right? So it will be 0.01 meter cube per minute, and this is mass flow rate. Mass flow rate, that is m dot is equal to this one, right? Mass flow rate we have already calculated as 0.1654 kg per second into 4 point, that is CP is already given as 4.179 kilojoule per kg into 65 minus 15 degrees Celsius. That is the total heat that is transferred between the inlet and exit of the water through the pipe. So that is 34.6 kilojoule per second. That will be 34.6 kilowatt. All of this energy, this energy that is being transferred to the water, this energy must have come from the heater. So this is the energy power rating of the resistance heater, because this is if we consider this as a diabetic system, so whatever heat is being supplied by the resistance heater is used for increasing the temperature of the water. So this is the, what is this? This is the power rating of resistance heater, right? Now what is been asked, the next question is the inner surface temperature of the pipe at the exit. So the for the inner surface temperature, we can take it from the surface heat flux, that is Qs dot. How we can calculate, like we already know the heat transfer rate, so from that we can calculate easily the surface heat flux. So that will be Q dot upon the surface area. So Q dot is 34.6 into 10 to the power 3 upon surface area we have already calculated as 0.471 meter square. This will be what? This is 73.46 kilowatt per meter square. Now, what we have to do? We have to first calculate like what equation we'll be using, that is whether this is a laminar or turbulent flow. First we have to find out that. So for that we need Reynolds number, and for Reynolds number we need the mean velocity. So the mean velocity will be the, from the volumetric fluid we can easily calculate the V dot upon cross sectional area, right? Because the volumetric flow rate is equal to velocity in the cross sectional area. Okay, so we have started with the previous class question. So the question is already available onto the screen. So we are just solving it out. Okay. So as I was already explaining, uh, the mean velocity for calculating the like which equation we'll be using, first we need to know the Reynolds number, that is whether the flow is turbulent or the flow is laminar. We need to know that. Okay, let me get your attendance first, just 1 second. I'm audible, right?
Yes.
Okay, then do you want me to repeat the question? Have you attended the previous class? I don't think so.
Not yet. Yeah, you can repeat once.
Okay, so is the question is visible on the screen? So one fluid is just like we are just inserting onto a pipe. There is a resistance heater that will give a constant heat flux, right? That we have already studied earlier, and we have
Yeah.
solved many questions on this part.
Yeah.
So fluid will be entering at 15 degrees Celsius, and as the heat is constantly supplied on this, so it will be exiting at a temperature, at a higher temperature of 65 degrees Celsius. So the first question that was provided to us was determine the power rating of the resistance heater. So how did we find out? What we did is that first we have found out the cross sectional area and the surface area, right? So from the MCP delta T, that is how much heat is being, like, see, the fluid is just entering and exiting, and whatever heat will be transferred to the fluid, that heat will be, like, if we consider this as an adiabatic system, so every inch of it, like every bit and piece of it, that heat will be used to raise the temperature of the fluid, right? So if we just calculate the energy that is being transferred to the fluid by MCP delta T, we can like equate that. We can clearly understand that how much power is being transferred by the resistance heater. So the first question is clearly answered over there. So now, first of all, is that, as you can see in the writing pad, that volumetric flow rate is already provided, that's 10 liter per minute. So from that we can easily deduce it at 0.01 meter cube per minute, correct? And now from that we can calculate the mass flow rate. So the mass flow rate is density into volumetric flow rate, right? So from that we can easily get the volumetric flow rate. Just 1 second. Okay, so from that we can easily get the mass flow rate. So mass flow rate we got as 0.1654 kg per second, right? And now from MCP delta T, M we have calculated, Cp is already given, and change in temperature is 65 from 15, it is 65, 65 minus 15. So from that we can get Q, and that is the power rating of the resistance heater, because that will be the heat that is supplied by the resistance heater to the fluid. Right. Now, what is the next question? Next question is estimate the inner surface temperature of the pipe at the exit. Okay. So, for that, first we need to calculate how much, like, we have found out the heat that is transferred. So, if we find out the heat flux over there, if we need to find out, so first we need to divide the heat transfer upon the surface area that we have already done. Okay. So, now, first, we need to understand whether the flow is laminar or the flow is turbulent. So for that, first we need to find out the Reynolds number. And for the Reynolds number, we need to find out the mean velocity. So already the volumetric flow rate is given. So from the volumetric flow rate, 0.010 meter cube per minute. And the cross-sectional area. So cross-sectional area is already we have found out as 7.069. If you are facing any doubt anywhere, you can stop me there and you can ask me the question. Okay. So this we find out to be 14.15 meter per minute. So if we convert it to second, this will be 0.236. I have pre-calculated it. You can try it at your home. And if you are facing any doubt, you can connect with me in the next class. Right. So Reynolds number will come out to be the mean mean velocity and the diameter into kinematic viscosity. It is 0.236 meter per second into 0.03 meter upon 0.658 into 10 to the power minus 6 meter square per second. So this will come out to be 10760 greater, that is greater than 10,000. So this clearly,
It will be dv rho by mu, no?
yeah, dv rho by mu, no? Rho, mu upon rho is mu, that is the
Okay.
kinematic viscosity.
The kinematic, yeah. Okay.
Yeah. So critical Reynolds number is provided to us as 10,000. So it is greater than 10,000, that is the flow is turbulent. Right. Now we have to find the entry length. So entry length is 10d for turbulent flow. We already have done this, like sir have already taught this in the class. So this is 10d is 10 into 0.03 into 0.3 meter. So sorry, this is equal to 0.3 meter. Sorry, just 1 second. Okay, now which is, this is much shorter than the total length of the pipe, so we will be assuming this as the fully developed flow. Even for turbulent fluid, like from the entry itself, like from the Reynolds number, we can clearly understand that this is turbulent flow. So for turbulent flow, as it is so much churning over there, so we can consider this as fully developed flow. So in most of the cases in turbulent flows, for flow inside a pipe, it is considered as fully developed flow itself. So now Nusselt's number is hd by k, and for turbulent flow, we know that it is 0.023, Reynolds number 0.8. In the previous class, I have already shown you this. So this Prandtl number 0.33, Dittus-Boelter equation. So this 0.023, this is Reynolds number is this much, 0.8 into 4.34 to the power 0.33. Right? This is this will come out to be 62.74. Now from here we can clearly find out H. This is 62.74 into K by D. K is already given as 0.631, so 62.74 into 0.631 upon dia. What is the dia? Dia is 0.03 meter. right? So this will come out to be 131.9.6 watt per meter degree Celsius. Okay, now we have to find out the surface temperature. So for constant heat flux on flow inside a pipe, we have already seen that we can write the surface temperature in terms of mean temperature and the constant heat flux as Qs dot upon H. I think sir have already taught this in the class. You have seen this equation, right?
Ma'am, I've not completed that lecture yet.
Okay then. You will see the whole derivation of this when sir will you will get the lecture. So for constant heat flux, that is when is flow is done, like when a fluid is flowing inside a pipe, that is and there are two conditions, right? One is constant surface temperature. When we will achieve constant surface temperature, when there will be change in phase. So we know that for phase changes, like when there is will be condensation, like that, so at that time the surface temperature will remain constant throughout the pipe. So by that way we can maintain the constant surface temperature for flow inside a pipe. And another thing is, if we use a resistance heater like that, we can maintain constant heat flux, because at every position the heat flux will be constant, because it is provided by the resistance heater itself. So in that case this Qs is constant, right? This Qs constant. Qs is the heat flux, surface heat flux that is provided. So this is constant. So we can write the surface temperature as this is the mean temperature of the fluid. So mean temperature plus the constant heat flux upon the heat transfer coefficient. So the mean temperature is given as 65 at the exit, right? So 65 degrees Celsius plus the heat flux we have already calculated here. That's why from the heat transfer we have already calculated the heat flux. So this will be 73460 watt per meter square upon 1319.6 watt per meter square degree Celsius. H we have already found out here. So this will come out to be 120.67 degrees Celsius. This is approximately equal to 121 degrees Celsius. This is the surface temperature. Okay, so any question related to this?
No, ma'am.
Okay, then I'll proceed to today's question bank. So this we already know from the previous class. These are the analogies that we are using for laminar flow and turbulent flow. For flow inside a pipe, and these are the equations that are using for the flow over a flat plate, right? So see, these are the two things that we are using. So if we will do if we will complete all the classes that sir have taught till assignment 7, then you will get to know these two equations. So for constant wall heat flux that I've already told you about, for that Nusselt's number we can take as constant to be 4.36, and for fully developed flow obviously, and for constant surface temperature, that is like when there will be conditions of condensation throughout the flow throughout the whole pipe, when the fluid is flowing inside the pipe. So at that case the Nusselt's number we can take as constant as 3.64. And for fully developed turbulent flow, the equation that we have just now used, that is the flow inside a pipe itself. So we can use Nusselt's number is equal to 0.023, Reynolds number to the power 0.8, Prandtl number to the power 0.33. And if this equation can remember, this equation can be used when the temperature difference between the mean fluid and the surface of the pipe is not much, like it will be small to moderate temperature difference. But if the temperature difference is used, then there will be a difference in mu, right, in viscosity. So we have to also add there mu upon mu w to the power 0.14. That is that will give us the Cedar-Tate equation, right? So many questions you will get on the basis of that, that you will find in the assignment. So Dietz-Bolte equation we can use for moderate or low temperature difference between the mean temperature of the fluid and the wall temperature of the pipe. Okay, so this is the first question for today's class. So consider both statement, and even if one of them is wrong, then mark the answer as false or else mark it as true. So first statement that they have made in the question is, in a thermally fully developed region of the tube, the local convective coefficient is constant and does not vary with x. Therefore, both the local friction factor, which is related to the local wall shear stress, and the local convection coefficient remains constant in hydrodynamically and fully developed for Prandtl number greater than 1. What is it saying, this statement? In a fully developed flow, thermally fully developed flow of a tube, the local convective coefficient is constant. That is, Hx is constant and does not vary with x. That is, H is constant. Therefore, the local friction factor, that is F, which is related to the local wall shear stress. Obviously, local wall shear stress T tau W upon half rho U square. We already know that equation. And the local convection coefficient remains constant in the hydrodynamically and thermally fully developed flow for Prandtl number greater than 1. Is it? And the second statement is, in turbulent flow, the intense mixing during the random fluctuation usually overshadows the effect of molecular diffusion, and therefore the hydrodynamic and thermal entry lengths are not the same and are strongly dependent on Prandtl number. Okay, so tell me whether any of the statement is false or not. I'll give you 1 minute to get enlightened on the question. Anyone? Are you having any difficulty in understanding? In turbulent flow, there is intense mixing during the fluctuation. So as it is, the churning is very heavy in turbulent flow. So the hydrodynamic and thermal entry lengths are not the same. And if not the same, are strongly dependent on Prandtl number. So whether the first line that stands is whether the hydrodynamic and thermal entry lengths are different in turbulent flow. And if it is, then obviously it will be dependent on Prandtl number. Okay, I'll give you 1 minute to understand the question and then answer. Okay, we can't give much time on this question. So first line is obviously true, but for the second line, as there'll be random intense mixing. So obviously the development of the hydrodynamic and the thermal boundary layer will be same, as it is different in the laminar boundary layer, except for Prandtl number is equal to 1. So if they are same, because they'll be mixing over there, so uh, it will be independent on Prandtl number. So the answer will be false. Let us proceed to the next question. In turbulent flow through a circular pipe, the Nusselt's number is related to Reynolds number by which of the following? This you will be surely able to answer.
RE raised to 0.8 as per Dittus Volter equation.
Yes, yes, is correct. So this will be option. I don't think I need to explain this. Then question number 3. Okay. So the local Nusselt's number correlation for a flow over a roughened surface is given as the following. Nusselt's number equation we already, like, it's already given in the question, how it is related to Reynolds number and Prandtl number. So what we have to find out here, the ratio of average heat transfer coefficient to local heat transfer coefficient. And okay, so for the starters, Nusselt's number is equal to HD by K, right? So when it is dependent on x, that is the distance from the leading edge, at that time it is local, and when it is calculated for the whole plate length, so then it will be overall. So we need to find out the ratio for the local to the ratio of the average to the local heat transfer coefficient. So we have to find out this h. So are you solving this? Okay, let me give you some, like, from hx, we can easily relate to Nusselt's number, right? But when it will be the average one, this we can clearly calculate as integration 0 to x of the local heat transfer coefficient dx upon x, right? So this can be used to find the average heat transfer coefficient. Now you can easily calculate, right? That is hx, how it is related to Nusselt's number. So we can write hx as a function of x, right? And average one also we can write as a function of x into some constant, right? Constant into some x to the power x raised to the power something. And here also we can write for the local one also, it will be like some constant, the constant will be same, but it will be into x raised to the power again something. So if we will divide hx, we have to find out hx average to local. So this will be something upon, so this will give some ratio, that is some value. So now you can easily solve this, as I've already explained how to solve this. I'll give you 2 minutes or 3 minutes at most to solve this, and then we'll carry on with the solution.
Ma'am, can you help in putting hx as a function of x? What will be the equation? for local heat transfer coefficient.
Yeah, so Hx is Nusselt's number into K by X, right?
Yes.
So this is already given as 0.04, Reynolds number to the power 0.9, and Prandtl number to the power 1 by 3. So this is Reynolds number also we can write in terms of
dV rho by
X.
mu. So in
Yeah.
that case, again x will be
So
there, right?
0.04, this is velocity into X upon nu to the power zero
Yes.
point 0.9. This we already know.
Hmm.
So this Prandtl number need not to be written, but you can also write and you can just replace it with some constant. This is Hx. So X upon K will also come. So this is K upon X, right?
Hmm.
The here K upon X will be there. Okay. So everything we can write in terms of constant, like here 0.04 V upon nu to the power zero point 0.9, Prandtl number to the power 1 by 3, K, and x to the power zero point 0.9 upon x. So this everything is constant, right? So we can just replace it with C1. So C1 x to the power minus zero point 0.1. This is local. Now just find it for average one and just find the ratio. Understood? Any doubt?
For average one, the length will be
Average one, you will just
okay,
find the average, right? You'll just average over the
how
whole.
the integration through integration. Yeah.
Yeah.
Ma'am, is it 1.11?
Mhm. It will be 1.1. Okay. Now this up to this we have already understood how to do. So this average, like we first find the average heat transfer coefficient. So how we will do that? As I've already said, we will just do the integration over the whole length, right? That is the average heat transfer is over the whole length, and that is just the averaging over x. So this will be hx dx till x. So this is 1 upon x, integration 0 to x. This is c1 x to the power minus zero point 0.1 dx. So this is c1 upon x, x to the power minus zero point 0.1 plus 1 minus zero point 0.1 plus 1 whole to the power 0 to x. This is c1 upon x, and this is x to the power zero point 0.9 upon zero point 0.9. This is 0 to x. This is c1 x to the power minus zero point 0.1 upon zero point 0.9. So this is 1.11 c1 x to the power minus zero point 0.1. So just we need to find the ratio now. Hx average upon local Hx heat transfer coefficient, that is 1.11 c1 x to the power minus zero point 0.1 upon c1 x to the power minus zero point 0.1. So this will just cancel away. This is 1.11. That is option B. Okay, so now let us proceed to the next question. Okay, so the experimental measurement of heat transfer coefficient for a square bar in gross flow is given by the following figure. Okay, so the length is 0.5 meter. It's already given, and two velocities are given. For each velocity, the heat transfer corresponding average heat transfer coefficient is given. Assume the following functional form for this case applicable with C, M, and N being constants and constant properties. So Nusselt's number is some constant into function of Reynolds number raised to the power m and Prandtl number raised to the power n. So we have to find h bar, that is the average heat transfer coefficient, when L is equal to 1 and V is equal to 15 meter per second. So this is very easy. Just we have to like find the ratio. Like first, based on the values that are given, we can just find out m, and when we will find out m, we can easily replace it in the main equation and with all the other values, and then we can find out the h bar, because h bar, that is average heat transfer coefficient, is Nusselt's number. Like Nusselt's number is equal to hd by k, so this will be Nusselt's number into k by d. Or like see c, we can figure out. So m, we can, like if we will find, write in terms of ratio with the values already given, so we can find out m. And again, if we like by taking one of the set of values as a reference point, and by taking the other, that is the unknown values, that is l is equal to 1 and b is equal to 50, by taking that values as other point, as point number somewhat 3, at that by doing like that, we can find out the unknown h bar. Any doubt? I've already explained how to solve this, so you are able to solve it, right?
So in that case, for let's say if I have to calculate m, I'll put n as constant for that case, and
You
then
don't require n, right? And we anyhow cancel out. In every case, n will be same.
Prandtl number will not be applied.
So
Okay.
write in terms of ratio, and over there you can find out m. And if you'll find out m, and in ratio c will also cancel out. So there is only one constant. So plug in that constant into the next equation. Take one of the known values, that is h1 and b1 or h2 and b2, as for the third case. Take that as one value and write again in the terms of ratio, and then you can find the unknown h. It's very simple. You don't need to calculate anything here. Just in terms of ratio, you write everything. You'll find the answer. I'll just come in 1 minute. You solve it. Hello. So have you solved it? Hello.
No, ma'am, currently. Mm.
You're solving, right?
Uh,
What problem are you facing?
I've done
Well,
the
relationship.
H1 by H2.
Uh-huh. Yeah.
Then,
H is related to velocity and length.
yes, velocity and length
Hmm.
to the power m
Hmm.
for a Reynolds number I've calculated.
Yeah, but it will
Then,
be HL, right? So HL will be related to VL.
okay.
See, this question is 4. So Nusselt's number is directly proportional to Reynolds number to the power m. So Prendel's number will just cancel out. So Nusselt's number is HL by K. So if K is constant, then HL is directly proportional to VL to the power m. Right. So this will be, if we write, now just make the ratio of it. So there will be one L here on the left side. So now just write in terms of ratio for case 1 and case 2. And for case 3, you already know M, and you can use any of the two cases, that is 1 and 2, 1 or 2, and solve for 3, case 3. Understood?
Yes, ma'am.
Just 1 second.
Ma'am, L value we have to put point 0.5, right? For both.
Hello? Yeah.
L value we have to put point 0.5, right?
L value. Yeah. L value are different for first. Yeah. For the first case, it is different, and for the third case, it is different. So put accordingly.
Okay. For first 1 and 2, both it will be point 0.5, but for third, we have to put 1 meter.
Hmm. Have you solved it?
Ma'am, the value of m is coming as 0.78.
Then use
Then
it for the next case, and use one or two case as reference, and do the same thing. Tell me what is the final answer.
ma'am, can you
Devika, tell me.
for the next the third part,
Hmm.
nu is equal to again hl by k
Hmm.
is equal to again that is proportional to vl.
Hmm.
Then in that case also, if we put L is equal to 1 and V is equal to 15,
Hmm.
15 to the power, we will get M, because L is again 1. So
Hmm.
we have just H is equal to 15 to the power 0.78.
Hmm.
But that is giving the value 8.
Uh, no, how come you are using that relation? You have to take one of the case one or case two, right? Otherwise, how you are using the ratio? The way you have done for case one and case two, the same way you have to do for case three. Because you don't know C, you don't know Prandtl number or N. So you can't use like just for part like case three, you can't find out because you don't know these values. So you just have to use the ratio form. Okay, let me solve this for you. So for the first case, this we already found out. So for case 1 and case 2, this will be h1 bar l1 and h2 bar l2 is equal to v1 l1 by v2 l2 to the power m. So from here we know h1 as 50, l1 as 0.5 and v1 as 20. Similarly, we know h2 as 40, l1 as 0.5 and v2 as 15. Now we'll just write this as 50 into zero point 0.5 upon 40 into zero point 0.5 is equal to 20 into zero point 0.5 upon 15 into zero point 0.5 to the power m. Now from here we get m as 0.78. Now for case 3 we have to find out where h we need to find out for l is equal to 1 meter and v is equal to 15 meter per second. So h upon, like, here we can just replace as h2l2 as hl, that is for case 3. Like we can simply write as h3l3 upon h1l1 is equal to V1, right? Yeah. So V3L3 upon V1L1 to the power m. Okay, so this we can simply write as H3 bar we need to calculate. So that is H1L1 by L3 into V3L3 by V1L1 whole to the power m. So m we already know. So this is H1 is how much? H1 is 50. 50 into L1 is 0.5 and L3, sorry, this is L3. L3 is 1. So 15, V3 is 15, L3 is V3 is 15, L3 is 15, sorry, L3 is 1 upon V1 L1. V1 is how much? V1 is
34.8
20.
we are getting. A.
Yeah, yeah.
Yeah.
So V1 is 20 into L1 is 0.5. So this is M is 0.78. So H3 will come out to be 34.3 watt per meter square Kelvin. So that is option A. Okay. So let us proceed to the next question now. So for question number 5, the characteristic length, the surface temperature and average heat flux for an object placed in an airstream of prescribed temperature and velocity is shown. Like for case 1, a small object of length L1 is 1 meter and the heat flux is given as 20,000 watt per meter square. The surface temperature was 400 Kelvin and the ambient temperature is 300 Kelvin and velocity of air is 100 meter per second. For the case 2, what happened is that the object, the characteristic length of the object is increased by a factor of 5. That is L2 have become now 5 meter and the air velocity is decreased by a factor of 5. That is V1 upon 5, that is 100 upon 5, that is 20 meter per second. Temperature has still remained the same. So what we have to find out? We have to find out the average convective heat transfer coefficient for the second case. For the first case, we can clearly find out heat flux is given as 20,000. So from that we can clearly find out the heat transfer coefficient. And in terms of ratio, if we write up for the second case, we can find out the heat transfer coefficient. Right. So just write in terms of ratio. The way we have solved now, the same way we can solve for H2. And now just we have to find out the heat transfer coefficient, right? Okay, so the heat transfer coefficient for case 2, we can write in terms of heat transfer coefficient of 1 into something. And for H1, we can clearly find out from the heat transfer, heat flux. Heat flux that is given as Q1 dash. So you can solve it, right?
Yes.
Yeah, do that. I'm giving you some time to solve it.
So H1 we are getting 200.
H1?
400 minus 300 into that is 100 and
How much?
20,000 will equate 200.
Yeah, 200. Then you solve for H2. Just find out the ratio, how H1 and H2 are related. Then you can easily calculate H2. Have you solved it?
Ma'am, I need help in finding that or relating that ratio.
Uh, okay. First, you differentiate the Reynolds number in terms of the velocity and nu 1 and nu 2. Hello. But
Yes.
okay. So what will be Reynolds number? Reynolds number will be VL upon nu. So V and L you already know upon nu. But nu in both of the cases are same, right? So the Reynolds
Yes.
number will be same. If Reynolds number will be same and Prandtl number also in both of the cases same because fluid is same, right?
Hmm.
So Prandtl number will also be same. So in that case, Nusselt's number will be same. And if Nusselt's number is same, then HL by K is same. And if HL by K is same, and K will also be same for both the case, so H1L1 is equal to H2L2.
Equal to H12.
So in that way, you can clearly relate them.
So H2 is 40.
Hmm?
H2 will be 40
Hmm.
because
Okay. Mm. So let me solve this for you. So Reynolds number in the first case is V1 L1 by nu 1. This is 100 into 1 upon nu 1, 100 meter square per second upon nu 1. Now for second case it is V2 L2 upon nu 2. This is 20 meter per second into 5 meter upon nu 2. That is 100 meter square per second upon nu 2. But nu 1 is equal to nu 2 because all the setup and system is same. Right, because why? Nu 2 is mu by rho and mu by rho will be same because the fluid is same. So therefore Reynolds number in case 1 and Reynolds number in case 2 is same, and Prandtl number will also be same, right? So Nusselt's number in case 1 and Nusselt's number in case 2 is same. And if Nusselt's number is same, H1L1 by K1 is equal to H2L2 by K2, right? So now K1 and K2 are also same. So that's why H1L1 is equal to H2L2. That is H1 upon H2 is equal to L1 upon L2. That is H2 is equal to 0 0.2 H1. Cos L1 upon L2. L2 is 5 times of L1. Right. So now Q1 is equal to H1 bar A1 Ts minus T infinity. Ts is 400, T1 is 300, and Q1 double dash. That is Q1 double dash is equal to Q1 upon A1. So A1 will cancel out, right? Right. So this Q1 double dash is given as 20,000. So H1 bar will come out to be 200 watt per meter Kelvin. So therefore H2 bar will come out to be 0.2 of 200, that is 40 watt per meter square Kelvin. This is meter square. So answer is A. Okay. Now let's go for the next question. So the Nusselt's number for laminar flow through a circular pipe is expressed as which of the following? Is a function of Reynolds number only, or Prandtl number only, or a function of Grace number? Grace number is Reynolds number, Prandtl number to the into d by L, and or Rayleigh number. Rayleigh number is obviously we know it is used for natural convection. So obviously Rayleigh number like option D cancels out, like it won't be the answer. So which is the correct option? Tell me.
A.
How A? How, A, tell me? Okay, so it will be okay. In the previous class, we already like got to know about this equation, right? For if the flow is not fully developed, we can write Nusselt's number as 1.86, Reynolds number, Prandtl number to the power d by L to the power 1 by 3. That means this is termed as Grade's number. So the option will be C, Grade's number, because obviously the Nusselt's number is not only a function of Reynolds number, and it is also not only a function of Prandtl number. It is a function of Reynolds number into Prandtl number both. Reynolds number power something or Prandtl number power something. So it will be option C. Now let us proceed to question number 7. Okay, so a 25 centimeter diameter stainless steel ball, density and Cp is given, is removed from the oven at an uniform temperature of 300 degrees Celsius. So it was placed in the oven and then it was removed. And when it was removed, its temperature was 300 degrees Celsius, uniform temperature, as depicted in the diagram. The excuse me, the ball is then subjected to the flow of air at 1 atmosphere pressure and 25 degrees Celsius with a velocity of 3 meter per second. So for the it is placed in a air flow whose temperature is 25 degrees Celsius. That is ambient temperature is 25 degrees Celsius, and the velocity of airflow is 3 meter per second. The surface temperature of the ball eventually drops to 200 degrees Celsius. Determine the average convective heat transfer coefficient during the cooling process. So obviously Newton's law of cooling will be using here. Assume a steady state operating condition and neglect the effect of radiation. Also consider air as an ideal gas and outer surface temperature of the ball to be always uniform. Furthermore, assume the surface temperature of the ball to be constant at average temperature of 250 degrees Celsius for the evaluation of heat transfer coefficient and use the value obtained herein for the entire cooling process. So all the properties are also given here, and dynamic viscosity and everything is given, and the Nusselt's number equation that we need to use here for Nusselt's number relation to Reynolds number, Prandtl number, and the difference in dynamic viscosity is also given here. Mu s is given and mu is also given. So everything is given. We need to first find out uh, what we need to find out the average convective heat transfer coefficient during the cooling process, that is h we need to find out, h bar. Understood or any doubt?
Understood, ma'am. In that case, Nu is equal to HD by K we have to put,
Yeah,
and
and
with
over there
given
you can find out
Prandtl
h.
number. Yes.
Okay, solve this. I will be back in 2 minutes. Okay.
Okay.
Have you solved it? Hello?
Ma'am, can you check H value is coming as 123.77.
H value is 1 how much?
123 it's coming.
No.
I have solved this Nusselt number correlation
Hmm.
based on that.
No, it won't be like that. Let me solve it. Like VD upon nu, Reynolds number. So this will be 3 into 0.25 upon 1.562 into 10 to the power minus 5. So this is 4.802 into 10 to the power 4. Now Nusselt's number is equal to HD by K is equal to 2 plus zero point 0.4 Reynolds number 0.5 plus 0.06 Reynolds number 2 by 3 Prandtl number 0.4 mu by mu s 1 by 4. I don't think I need to put the values. Everything is given. Like Reynolds number will be this. Prandtl number is 0.7296 and mu is given 1.849 into 10 to the power minus 5 and mu s is given as 2.76 into 10 to the power minus 5. So if we'll put everything on place, it will come out to be 135. Okay.
Okay, I made a mistake in putting mu value just because I forgot 10 to the power minus 5 will cancel out in the ratio.
10
I
to the
understood.
power?
So mu by mu s ratio, I was
Hmm.
getting a bit larger because I forgot the 10 to the power minus 5. So I think the value
Okay,
is
okay.
higher in that. So I
Then
understood. Yeah,
it
yeah.
doesn't matter if you will forget 10 to the power minus 5 also, it will be one, it is ratio, right? So it
Yes,
will
but in
be
one I have
plus.
put and another I have forgot. So then the value will
Oh,
become much larger
then
in
it
the
will be
yeah.
very
So I
hard for
I
the
understood where I
okay.
went wrong. Yeah.
Okay, okay. So then H is equal to Nusselt's number K upon D. So Nusselt's number will be like K will be 0.02551, right? Yeah. So Nusselt's number is 135 and D is 0.25. So this will come out to be 13.8 watt per square Kelvin. So this is option A. Now there is a second part of this question. Let us proceed to that. Estimate how long this process of cooling would take place. So this is a bit tricky. That is, as it is said in the question that it will cool down from 300 to 200, right? So how long will that process take place? So how we will proceed towards that question? Can you tell me? How we will proceed to find that?
We need to calculate heat flux.
But time you need, na?
Okay. So
One, you will be using Newton's law of cooling. So Newton's law
yes,
of cooling
yes,
will give you average temperature, average heat that has been transferred.
yes.
So average heat that has been transferred and total heat that will be transferred. How we will calculate that? That is total heat is been transferred is how much the temperature is been decreased. That is from 300 to 200. How much the temperature is decreased. So that will be the total heat, and that heat that has been decreased within the body is equal to the heat that is taken away from the body to the surroundings. That will be given by the Newton's law of cooling. That is one equation will be average heat that is given as HAS into TS average minus T infinity. That is if this is the ball and this is the ambient. The heat there will be a temperature change within the body itself with time, and there that heat will be taken away from the body to the surroundings. That is this heat will be equal, all both of them will be equal. Sorry, not equal, that is oh, wait. So this temperature change, that is from 300 to 200 degrees Celsius, that will give you the total heat change, that is MCP, that can be find out from MCP delta T. for any body when it is changing the temperature in time, in specific amount of time. So you can calculate from mcp delta t, the change of heat within the body itself. And at the same time it will dissipate heat from the body to the surroundings. So that will give you the average heat that is being transferred from the body to the surroundings. So first we found Q average by Newton's law of cooling, QAST, HAST, TS average, that is surface temperature, average surface temperature to infinity. So this will be average surface temperature as it is indicated in the question. Where's the question? As it is indicated in the question, the average surface temperature is taken as 250, right? 250 degrees Celsius. That is 300 plus 200 upon 2. This is the average temperature. So if we consider 250 degrees Celsius at average temperature, and infinity to infinity is how much? 25 degrees Celsius. And surface area we can calculate for the ball. And H is also just one second. Yeah. So
13.8 we
H
have
is also
calculated.
given. Yes.
Yeah.
So H is given as 13.8. So from there we clearly can calculate something what? That will be the average heat that is
60,
transferred.
60.93 we are getting.
How much?
60.93.
609.3. Somewhere you have mistaken one point. So it will be
200,
609.52.
250 minus 25
250
into
minus 20.
13.8 we have H.
Hmm.
And area is for this, it is pi d square.
Pi d square. D is 0.25.
0.25, yeah. 0.25.
So it will be 0.1963. So, okay. Now, we have to find the total heat transfer from the ball, which is simply the change in the energy of the ball as it cools down. So, if a ball mass, that is any mass, will change the temperature of the body will change in time, we can calculate with mcp delta t. So, first we have to calculate m. So, what is m? M is density into volume, and volume we can easily calculate as pi by 6 d cube, as it is a sphere, right? So it will come out to be 65.9 kg. I won't calculate the rest, you calculate and tell me the answer. So the total heat that is been transferred, like total heat that is being transferred from the ball itself, that will be mcp delta t. Delta t is t2 minus t1, that is 300, 200. T1 is 200. So this will come out to be something. You calculate this first. Now, what will be the time? What will be the time? In this calculation, we assume the entire ball is at 200 degrees Celsius, which is not necessarily true. The inner region of the ball will be probably at higher temperature than its surface. Obviously, the inner region will be 300, and gradually it will decrease to 200, right? So
Yes.
when it will decrease to 200, at any instant of time, the inner temperature will be higher as compared to the outer temperature, because
Yes.
from the outer there will be also the heat will be
Convective
also
heat
taken away to
transfer.
the will be taken away into the atmosphere. So with this assumption, the time of cooling is determined, like here we will get some value, but this is in terms of joule, right?
It's
And
3163200.
how much?
3163200.
uh-huh. So this will be in terms of joule, and this will be in terms of what?
Yes.
Okay. So what means joule per
Joules
second?
per second.
Hmm. So clearly we can, if we will do unit balance also, we can clearly determine from both of them the time. Second, right? So what we will do, Q total upon Q average. There is a total heat that is changed in the body by mcp delta t. So that will be 3163200 upon the total heat that is being transferred by the body to the atmosphere.
Yes.
So that is how much it came?
609.3.
609.609.52. How much it is coming?
5191.
Joule per
5190.
second. So this will be 51.
90. Somewhere.
Yeah. So this will be seconds. So this is option B. Yeah. Done. Now This part is also done. Okay, now with this question, the value of Nusselt's number for a system where a sphere is placed inside a pool of stagnant water. What is the value for the Nusselt's number for this? Sir, I've already taught this in the class, right?
It is 2 because the rest of the terms will
Yeah.
be changed to 0.
So, yeah, so this will be A. Okay. Just 1 second. Mhm. Now let us proceed to question number 10. Okay. So in this problem, what is there? An engine oil is flowed over a flat plate. The temperature of the surface of the flat plate is 20 degrees Celsius and engine oil is heated up. That is the temperature, that is the heat will be transferred from the engine oil to the flat plate. And the engine oil is flown at a velocity of 2 meters per second. Determine the rate of heat transfer per unit width of the entire plate. And that is the rate of heat transfer Q we need to find out. And the properties are also given. So what will be the rate of heat transfer? It is fairly simple question. You try to solve it by yourself. I am giving you some time. There is all the equations we already know. First, we need to find out the Reynolds number and what the flow is, like whether the flow is laminar or turbulent. We'll find out from that. So based on whether it is laminar or turbulent, we'll be using the corresponding equations. That is these equations. Let me show you. You have already come across these equations. Yeah, this one. This is the Nusselt's number. This is notice for one thing, that is this is Nusselt's number local. And when we need to find out here the average Nusselt's number, that will be twice in case of laminar and 5/4 in case of turbulent. So both of the, like, based on whether it is turbulent flow or laminar flow, we'll be using the corresponding Nusselt's number. Write this down and
Yes.
then just the Nusselt's number, nothing else you can now. So based on whether it is laminar or turbulent, we will be using corresponding average Nusselt's number value, like equation. And
Yes.
once you know that, then you can clearly deduce the heat transfer coefficient from there. And once you get the heat transfer coefficient, you can easily find out the heat transfer, rate of heat transfer. It's fairly simple.
Yeah. Ma'am, can we go back to the question I've written?
Yeah. So solve this and tell
Yeah.
me which of the option is correct.
Ma'am, the Reynolds number is coming as 40,240,
Hmm.
which is greater than 10 to the power 5. So the flow is turbulent.
40,000, no, it is less than 5 into 10 to the power 5, right? It is 4.024 in 10 to the power 4,
Yes.
correct? So it is less than 5
Yes.
into 10 to the power 5.
Oh,
So the flow will be laminar.
5 to 10 to the power 5. Yeah. Okay.
Then use the equation accordingly.
Yeah. Ma'am, can you cross check? Nusselt number value is coming 956.45.
Nusselt number. No, 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 no.
Just a second. 4024.
Check it again.
The relation is 0.332 into Reynolds to the power 1 by 2, Prandtl 1 by
0.332,
3.
it will be twice, right? I told you, na,
Yes.
0.332 is local. We have to find the average. That will be twice for laminar flow. So it will be
So,
0.364. Reynolds number 0.5, Prandtl number 1 by 3. Use that equation.
ma'am, can you repeat again? Sorry.
Uh, for laminar flow,
Hmm.
the average Nusselt's number is twice of the local Nusselt's number, right? So it is local
So,
Nusselt's number 0.332.
956.45 into 2 is 1912.
It will be 191.
12,
Proceed
okay.
further.
Ma'am, it's 11.01.
Yeah,
C.
correct, correct. Kilowatt.
Yes, it's coming 11016 watt.
Huh. Okay. So first Reynolds number will be VL upon nu. This is 2 into 5 into 2.485 into 10 to the power minus 4. So this is 4.024 into 10 to the power 4. This is less than 5 into 10 to the power 5. So the flow is laminar, right? So Nusselt's number is equal to 0.664, Reynolds number 0.5, Prandtl number 1 by 3. So this will come out to be 1912.8992 as you already found out. So H is Nusselt's number K by L. So this will come out to be 55.09 watt per meter square Kelvin. So Q is HAS T infinity minus TS, right? So if we will put all the values, surface area is 5 into 1 because it is said per unit width. So width we have taken as 1. So this will come out to be 11.018 kilowatt. That is option C. Okay, we will proceed with one more question and rest of the questions we'll do next week. So the Peclet number and the Grates number are the function of which of the following dimensionless numbers? What we know about Peclet number? What is Peclet number? Tell me. Do you know? Hello? Hello?
Packlet number is LV by D, that is diffusion. dispersion. That is Reynolds number into Prandtl number.
Yeah. So which of the following option will it be? Gates number is a function
First
of
one,
what? And first one.
first one is
Hmm. It will be first one only. So Peclet number is a function of Reynolds number and Prandtl number, and
Yes.
so obviously it will be number one. But we are so obviously if you will know the Peclet number also, then also you know is option one, because others won't satisfy. But if we find out Grace number also, we already heard about, like already have read about it na, and in another question, that Grace number is equal to Prandtl number, Reynolds number, d by n. That is a function of Peclet number, right? So it will be option A. Now, should we do one more question today? Let us proceed with this question for last, and then we have one more question. We'll do it on the next class. Okay. So, for the question number 12, what is there? Water at 20 degrees Celsius flows through a 2.5 centimeter internal dia of 1 meter long pipe whose surface is maintained at a constant temperature of 50 degrees Celsius and at a velocity of 5 centimeter per second. Velocity of the water flowing is 5 centimeter per second. Determine the outlet temperature of water. Determine the outlet temperature of water assuming fully developed hydrodynamic boundary layer. Okay, so we will consider the boundary layer to be fully developed and determine the outlet temperature of water. Mm, the initial temperature is given, the surface temperature is given, the diameter of the pipe is given, length of the pipe is given, and the velocity is also given. The mean bulk temperature is also given as 22.5 degrees Celsius. Density, viscosity, the Cp, that is the heat capacity is also given, and thermal conductivity is also given, and Prandtl number is also given. Now, for constant wall temperature, for like constant wall temperature phenomena we already know, and for constant wall temperature to satisfy this L by T upon Reynolds number into Prandtl number should be less than 1. So if we will find out this, and if it comes to be less than 1, then obviously it will be constant wall temperature. And then if this is satisfying constant wall temperature, then we can use this equation. Nusselt's number, average Nusselt's number is equal to 1.67 Reynolds number into Prandtl number upon L by T to the power 0.333. Understood? So what we need to determine? We determine the outlet temperature of water. Understood? Or do you have any doubt?
Ma'am, after this LD, if we have this LD by L by D into divided by R into Prandtl less than 0.01,
Hmm.
then we can use the NU average. So we'll get HD by K,
Hmm.
we'll get H.
Yeah,
Then,
we'll get H from there.
so HA delta T
Then we can do energy balance. That is MCP delta T is equal
is equal
to
to HA delta T.
HA delta T. Yeah. So in HA delta T, it will be surface temperature minus mean temperature of fluid. And for MCP delta T, it will be inlet to outlet temperature. That is T naught. T outlet to inlet. That is inlet temperature is already given as Ti. So T naught minus TL. So from there we can clearly find out T naught. Right? Try this.
The the average temperature will be mean bulk is already given 22
Yeah,
point.
it's
Yeah.
already given. See, here we won't be using as the mean bulk temperature that is given. So it will be mean bulk temperature. We will take as what? Just one second. Mean bulk temperature will take as uh, 20. That is the water temperature at the inlet plus outlet, cause we don't know T naught, right? So T naught we need to find out upon 2. Otherwise, if at 22.5 we can clearly easily calculate, but here we won't be using like this is the initial guess. We can take 22.5 as initial guess, but T naught as we don't know, we can't finally say that T naught will be like T mean will be 22.5. These are the mean bulk temperature that is provided in the question. But for finding out the T naught, we need to write mean temperature in terms of inlet and outlet temperature. That is T naught plus T I upon 2. Ti is already given as 20. Understood? Right, in terms of this,
Yeah.
and in MCP delta T also you will get T naught minus Ti. So if you will solve this, you can find out the T naught. Solve it. I'll just take one call and come back, okay?
Yes.
In 1 minute. Have you solved this? Hello?
Ma'am, I got Nusselt number value as 9.998.
Nurse's number 9.998. Yeah.
And value of H is 240.8.
Then do the energy balance.
Yeah, Q is it. Ma'am, for mass, for energy balance, HA delta T is equal to MCP delta T. But
In HA, it will be like it will be convective rate of cooling, right? So that will be in terms of surface temperature of the pipe and
minus
the
no.
minus the mean temperature of the fluid.
Yes,
So mean
that
temperature of
value
the
is
fluid will be inlet, like inlet temperature of fluid plus outlet temperature of fluid, that is T naught, Ti plus T naught upon 2. And for MCP delta T is the total for any body, we know that the total temperature change in the body itself. So it will be T out minus T in. So from that you develop one equation, and from that you can put all the values and you can calculate
ma'am.
the
But what will be the value of M?
M is you can calculate from
Rho
velocity.
into V. Yes, yes,
Yeah.
yes. Rho into V, na?
Hmm.
Yeah.
Rho into volume. Rho into volume into velocity. Sorry, rho into volume, and volume is area into velocity. So area is pi d square by 4.
Ma'am, this will be cylindrical, no? If 1 meter long pipe is there, then pi dl will come as area.
Hmm?
It is through 1 meter long pipe, so it will be cylindrical, no? Pi dl.
Yes, it will be cylindrical, but the flow of, that is the heat transfer, will be in pi d square by 4 direction, right? Like, see here, heat transfer, like when it will be MCP delta T, the heat transfer is in cross sectional area. It is in the bulk flow of fluid, right?
Okay.
The heat transfer through convection or through conduction is in the pi dl direction. That is
Okay.
the
Okay.
like surface area, lateral surface area. But
Yeah.
when it will be bulk flow of fluid, it will be always in the cross sectional area direction. That's why when we take for, like when we do the overall mass, that is what is the overall mass flow rate or something, it will be in the cross sectional area direction.
Okay.
We consider that as a plug of fluid, right?
Yes.
That's why we can take the, otherwise if it is like it, if it is not, we don't, we consider it as fluid, like not a plug of fluid, then the temperature may change, right?
Yes.
So that's why we are considering it as a plug of fluid, and that's why we can consider as MCP delta T. But it will be in the cross sectional area direction. So the area will be pi d square by 4. Have you solved it?
Just to
Okay.
ma'am, since it is given mean bulk temperature, we don't have to put that same value. We have to put 20 plus T naught for any
Yeah, yeah, yeah,
this.
yeah. We don't know the outlet temperature, right?
Okay.
These are the actually we have to, if for any question na this, we got charts of this viscosity or density or everything, so
Hmm.
they give some mean bulk temperature and we have to find out that, but I've already provided this in the question, so you don't need to consider this mean bulk temperature. So we already don't know the outlet temperature, so we'll be considering mean bulk temperature as Ti plus T naught to find out the actual T naught. This is just an approximate mean bulk temperature that is given.
Ma'am, while equating MCP delta T, uh, mass is coming as 49.875.
I have not separately considered that actually. What you got the final T naught?
Ma'am, actually, I'm stuck in MCP delta T is equal to HA delta T, wherein the left hand side
HAS
value.
AS will be the HA will be, that area will be the surface area. That is the pi dl, because the heat transfer, convective heat transfer will be in the aerial direction, right? And when we'll be considering MCP delta T, at that time it will be, the area will be pi d square by 4. That is the cross sectional area. In whenever we will be considering MCP delta T, that mass, that is it will be, it will be the, see how we are considering here pi d square by 4. MCP delta T is like, if we will consider this as plug of fluid, this is volume into density, right? But this
Hmm.
volume we are considering as velocity into area. So velocity is in this direction. Like let's suppose if this is x, velocity is in
Hmm.
this direction meter per second. That is, this direction we have already considered. So that's why we are considering the cross sectional area. Understood?
Yes.
Because volume will be cross sectional area into this length, right? And this length we are already considering in terms of velocity as meter per second. So that's
Yes.
why we are considering cross section area here. So cross section area into velocity into density. But when we consider HAS delta T, that will be surface area, that is this area, that is pi dl. Have you solved it now?
Uh, no, ma'am. That PyDL one and do just a second.
Hmm. Is it done?
And then last part. Ma'am, it's coming 47 degree.
47. No, it
Mm.
won't come like that. You have done some mistake. Check it. Okay. Let me solve it for you and you can check it once back at you.
Yes.
Okay. So first Reynolds number will be du rho upon mu. So if you'll put everything, it will be 1.313 into 10 to the power 3. So this is less than 2300 for internal flow. So this will be
Mm.
laminar. Now for laminar, L by D into Reynolds number into Prandtl number. So this will, if we'll put every value, it will come out to be 4.635 into 10 to the power minus 3. Because this Reynolds number we already know, Prandtl number is 6.575, L is 1, D is 0.025. But this is less than 0.01, right? So we can use the Nusselt's number equation that is provided. That is Nusselt's number is equal to 1.67 Reynolds number, Prandtl number upon L by D to the power 0.333. So this will come out to be 9.998. Now H will come out to be 240.754 watt per meter square degree Celsius. Now energy balance when we will do, this will be MCP T naught minus Ti is equal to HAS minus Tm. Okay, now Tm is Ti plus T naught by 2 and M is pi d square by 4 into density into velocity, right? And this surface area will be d pi dl. So if you will put every value, this will, let me write the values for you. So pi into 0.25 square upon 4 into 997.5 into 0.05, 0.05 is the velocity into 4181, that is Cp,
Ma'am,
into
dia is point zero
T
two
naught.
five, na?
Huh?
Dia is 0.025, na?
This velocity, na?
No,
This
no,
is
on
radius.
the 0.025 it is given.
Yes. So diameter we have taken 0 to 5 only. Where?
Ma'am, point 0.025 it is given.
Oh, this will be 0 only.
Okay.
This I have mistakenly written like that. No problem. Mm, just 1 second. Let me calculate that again. Then okay, 4181 T naught minus 20. T naught minus 20 is equal to pi into 0.025 into 1 into 240.754 into 50 minus 20 plus T naught by 2. Okay, I think so. This 0.025, there I have done some mistake. Let me solve this again. So what value did you get for this? This whole thing. Wait. Okay. This whole thing. What value have you got?
Mm,
Find out the value.
104. Sorry, it is point. 50 minus this, no?
400.
104.26.
Hmm? Into 4. Just 1 second. 4181, right? 4 CP is 4181. 4181. 102.36. Yeah. This is 102.36. Now let me solve for this pi into 0.025 40.754. This is 18. This whole thing will come out to be 18.908, right?
Yes, it is coming.
Okay. So then if we will solve for this, this will be
102.36 into x minus 20 is equal to, this is 18.908 into 50 minus 20 plus x upon 2. So now we will solve. Yes, this will come out as 25.07 T naught. Did you get this?
Ma'am, I had the MCP delta T. I considered 50 minus T naught, so that's why it was getting.
Uh,
It's T naught minus 20. We have to consider.
yeah. Okay. Then you will get this 25.07, the final answer. Okay.
Hmm.
Okay. I'll proceed to the next question. You just take a screenshot of this and try to solve it. We'll talk about this or solve it in the next class. Take a screenshot and try to solve this back at home.
Okay.
Okay, done. Have you taken?
Yes.
Okay, then I'll meet you all next week. Bye bye.
Thank you. Bye.